When an application is using all of its available resources, that application needs to be scaled. Scaling an application means giving it more resources, typically servers. Autoscaling is an engineering practice where an application is automatically given more or less resources based on how healthy the application performance is at a given time. If an application is unhealthy, you might scale up. If an application is very healthy, then maybe you can scale down and give it less resources. Applications on Heroku have access to autoscaling. Heroku users don't need to worry about provisioning new servers manually because the platform does it for them. In this episode, we explore how Heroku built autoscaling. Andrew Gwozdziewycz is an operational experience engineer with Heroku, and as he describes, autoscaling requires frequent health checks of an application. Since thousands of applications are running on Heroku, a metrics pipeline using Kafka and Cassandra supports the high volume of health check data that's constantly pulling data from those running applications, piping it through Kafka, and storing it in Cassandra. That data pipeline feeds into the decision process for when an application actually needs to scale. This was an enjoyable and entertaining episode about infrastructure at a large platform as a service provider, which is Heroku. Full disclosure, Heroku is a sponsor of Software Engineering Daily. Life is too short to have a job that you don't enjoy. If you don't like your job, go to hired.com/sedaily. Hired makes finding a new job enjoyable, and Hired will connect you with a talent advocate that will walk you through the process of finding a better job. It's like a personal concierge for finding a job. Maybe you want more flexible hours or more money or remote work. Maybe you want to work at Facebook or Uber or Stripe or some of the other top companies that are desperately looking for engineers on Hired. You deserve a job that you enjoy because you're someone who spends their spare time listening to a software engineering podcast. Clearly, you're passionate about software, so it's definitely possible to find a job that you enjoy. Check out hired.com/sedaily to get a special offer for Software Engineering Daily listeners. A $1,000 signing bonus from Hired when you find that great job that gives you respect and salary that you deserve as a great engineer. I love Hired because it puts more power in the hands of engineers. Go to hired.com/sedaily to get advantage of that special offer. And thanks to Hired for being a continued longtime sponsor of Software Engineering Daily. Andrew Gwozdziewycz is an operational experience engineer with Heroku. Andrew, welcome to Software Engineering Daily.
Hey, thanks for having me, Jeff. It's good to be here.
Yeah, it's good to have you. So today we're going to talk about autoscaling, and I'd like to start with a top-down approach, and then we're going to get into how to build autoscaling. What is autoscaling?
Well, I mean, that's kind of an interesting question. It seems like it should be simple. The basic idea of autoscaling, the basic premise is this idea that you don't really want to have idle servers, right? And so if you can right scale to the exact right amount of resources that you need, then you're probably going to save some money, and everyone likes that.
Well, what are the conditions when an application might need to scale up?
So I kind of like to think of it with this story. So the story is you're using Chrome, or maybe you're recording a podcast or editing a podcast, and your fan comes on, right? You have a laptop, the fan comes on, it starts whirring and whirring and whirring, and it'd be kind of cool to be able to just like drop another CPU in your machine and move some of your other applications there, and then you become responsive. So kind of autoscaling is the same sort of thing. You have like one resource being used a ton, and you want to kind of just split that load a little bit differently amongst multiple resources instead.
Absolutely. So there are plenty of people who have applications on a hosted service like Heroku. Why is autoscaling relevant to somebody who is on one of these platform as a service services?
Yeah, so I mean, I don't think it's specific just to Heroku or or even just a platform as a service in general. Amazon has autoscaling, which we definitely consider as infrastructure as a service. But I mean, they're the same sort of thing, right? So for Heroku, what's interesting is that our value proposition has kind of always been, hey, you can adjust the amount of compute power that you have just by moving a slider back and forth on a website, or you can adjust the size of the dyno, how much compute power by moving a drop down. So I think like it's been a long time coming, and I think it's kind of just part of our value proposition that we've just never really fulfilled.
Now, in order to know when an application should be scaled or should not be scaled, if somebody's on Heroku or another managed platform as a service, the like you said, the value proposition is basically that it's very straightforward to configure it from the user's point of view, and on the back end, the platform as a service is taking care, or the infrastructure as a service, whatever you want to say, is taking care of all the complexity of that scaling up and down. And in order to do that accurately, the service provider, such as Heroku, has to track the health of that application. What are the metrics that need to be tracked in order to get the right amount of observability in order to do auto scaling on the back end?
Yeah, well, to be honest, I don't really have a clear understanding yet, but I can tell you what we do have and what we're starting to use and starting to think about. I mean, the basic metrics that we have are the same metrics that any sort of system would monitor. Memory, your load averages, different errors that you might have. For dynos that serve requests, which is really the only thing that we're auto scaling right now, some sort of latency, the error rate of, different statuses. So like throughput, response time. And yeah, I mean, if you're talking about, like scaling different types of things, like let's say that on Heroku, you have a common thing where you'll have like a worker process that reads from a queue, like Sidekick or, like even Redis or something. And it seems to me that having some sort of like throughput metric or queue depth from like, Sidekick or something, that could give you some pretty good insight into auto scaling, like those different types of processes. So that's kind of what I would suggest here. The thing that we do at Heroku for latency, we just have a median and like the P95, and that's most of what we store. We do store those pretty accurately because we make use of those pretty well. The other thing that's interesting about this is, like, at what resolution do you store this stuff, or at what resolution does it make sense to use this stuff, I should say. And right now, we're doing all of our monitoring at a 1 minute resolution. And that's, for a few reasons, not the best, but it's what we have, and it's kind of an acceptable trade-off at the moment.
So I have an application at the company that I'm building, and it has a web interface. It also has a mobile interface. So these things have different access patterns to the same backend. I am curious, what is the amount of granularity that you want to expose to the user? Because there are going to be certain times where the user wants to troubleshoot something, and I can imagine a scenario where, okay, I want to separate the requests from mobile from the requests from the web front end, and in order to diagnose aspects of my application, in order to know how I should set up auto scaling. Is that an amount of granularity that you want to expose to the user when you're building this? Because I think of Heroku as kind of an interesting, you make trade-offs between how much you want to expose to the user in the default modality versus how simple you want to make things. So what is the right balance between, because you're talking about different things that you're tracking for the purpose of auto scaling. I'm kind of curious, like, which of these things do you want to expose to the user so that the user can do what they want to with that data as well?
Yeah, so in our case, we don't really have anything that we don't expose to the user. I should rephrase that. So there are some things that would be harder to get for a user on Heroku, but there's nothing that they can't get. We actually track a time series of the number of dynos that are running at any given time, which you would have to work pretty hard to extract that yourself, because you'd have to, obviously keep track of like how you've scaled and things like that. But other than that, our model right now is be as transparent as we possibly can. So we have a product called Dashboard Metrics, which exposes all of the things that we basically collect in a nice interface. And that's the same exact data that we're using right now to autoscale. No tricks, nothing up the sleeve.
Got it. All right. Well, since we're talking about how to do the autoscaling, there is this process where you need to take the data. So you've got all these applications that are running across Heroku's platform, and all of these applications have different health data. That health data needs to get piped to essentially a separate system that can analyze the application from the outside looking in and say, okay, this application needs to be scaled. And this is kind of a metrics pipeline in your case. Can you describe the high-level overview for how that metrics pipeline works and what it's trying to accomplish?
Yeah. So ultimately, what ends up happening is we read log data. All of the data that we get is basically sent to us as like syslog, basically. That stuff gets processed via a tool we call Ingress, and we dump everything, like all this raw data, all these raw measurements that we get, we dump it into Kafka. We have some processes that read those Kafka queues and produce summaries. Those summaries eventually get written out to Cassandra. And there's other processes that will read the Kafka queue to do things like alerting or auto-scaling on those metrics.
Okay, so you mentioned that you're on Cassandra right now. I know that there was a progression of different databases. Let's talk about the database requirements for this system, and then we'll talk about the progression of the databases. What do you have to build, or what are the requirements for this database in order to store this massive amount of health data?
Yeah, so it's kind of interesting. There's a big trend these days in sort of like time series databases. There's products like OpenTSDB, and Facebook has something along these lines.
RocksDB?
Well, there's RocksDB, and then there's a paper that they published recently. I think it was called Gorilla, but they've changed the name of it now. I think something with a B, which I can't remember the name of. It might actually use RocksDB under the hood, but I think their primary focus was put everything in memory.
Okay.
So there's InfluxDB. That's the popular one that we started with, which we'll get to in a second. But yeah, I mean the property of all these, or the thing that, or the reasons that there are so many of these things now, is because people are really obsessed with this idea of like write throughput. So you want like the highest level granularity, or the lowest level granularity that you can get, like sub-seconds in some case, right? For these types of metrics. And so you need to be able to write things as fast as possible. The reality is, like, you're most likely not going to be reading all of the data that you're writing. So you can tolerate like some slower reads as long as you can write fast. So those are the trade-offs that are typically made. We generate way too much data to be able to read it all, back out again at some point. So for us, though, we took a slightly different approach, and we said, hey, you know what? We don't really want to store everything like raw. We can store aggregated stuff, and that will actually cut down on our requirements significantly. It's easier to compute things and then store in a like a 1 minute resolution than to try to worry about collecting hundreds of thousands of data points and then rolling them up on demand. So that's kind of the approach we took.
And what you're describing sounds like a good application for Kafka streams. Do you use those?
We're not, although they came out a little bit after the stuff that we started doing. I don't know too much about Kafka streams, but I think we're probably pretty close to doing the same thing as what streams provide.
Ah, interesting. So you just implemented it anyway.
Yeah, I mean, it's probably close. It's definitely not, like to spec or anything like that, right?
Yeah.
If there is even a spec.
Where are you doing that aggregation? Because I can imagine you get these things aggregated. You could aggregate them before they go into Kafka. You could aggregate them right after Kafka, or you could put them into Cassandra and then aggregate them and then delete the Cassandra entries. What are you doing exactly?
Yeah, so that's sort of the thing. Like, a lot of those time series databases, they'll write the raw data and then do the aggregation, like when you're pulling stuff out. And so our approach is actually, well, we have all this data in Kafka, and we'll have like a topic named like load average. That'll store the raw data before it's processed. We'll take a process which is just running on Heroku, the Heroku platform. It will read that Kafka queue or that Kafka topic and summarize it in memory and then write it back to another topic, say 1 minute load average, right? Then if we want to do like a 10-minute aggregation, we'll read that 1 minute topic, aggregate it to 10 minutes, write it to a 10-minute topic. So it's basically just like this zigzag of you pull the data out of a topic, write it back to another topic, pull the data out of this other topic, that's like a higher granularity, and write it back.
Wow.
So it's kind of nice. But I mean, at any given point, like we have different amounts of data or at different granularities sitting in Kafka.
Simplify continuous delivery with GoCD, the on-premise, open-source, continuous delivery tool by ThoughtWorks. With GoCD, you can easily model complex deployment workflows using pipelines, and you can visualize them end-to-end with its value stream map. You get complete visibility into and control of your company's deployments. At gocd.io/sedaily, you can find out how to bring continuous delivery to your teams. Say goodbye to deployment panic and hello to consistent, predictable deliveries. Visit gocd.io/sedaily to learn more about GoCD. Commercial support and enterprise add-ons, including disaster recovery, are available. Thank you to GoCD and thank you to ThoughtWorks. I'm a huge fan of ThoughtWorks and their products, including GoCD, and we're fans of continuous delivery. So check out gocd.io/sedaily. Let's talk a bit about how you got to where you are today, because you're saying but I guess you're saying the ultimate result of that is you've got some topic that has an aggregation, and then that topic spits it out into Cassandra. Is that right?
Yeah, basically. I mean, that's the basic premise.
Okay, so on your way to this current architecture, there was a point at which you had InfluxDB, there's a point at which you had Postgres. Eventually, you got to this Cassandra plus Kafka solution. Can you explain the progression in more detail?
Yeah, so I joined Heroku, I guess it's almost 3 years ago. I think it'll be 3 years in June. And my first project was to help ship the first version of dashboard metrics. So dashboard metrics came out of this idea that we're only ever showing metrics in a log stream. And wouldn't it be nice if we could actually give someone a visual representation of what those metrics are in a log stream, such that they don't always have to go to an add-on to do this. Heroku has this concept of add-ons, which are basically partners that you can easily set up through Heroku, like through the Heroku CLI. So the decision to use InfluxDB was kind of an obvious one at that time. It was the kind of the new thing on the block. It did exactly what we needed to do, and it supported this idea of continuous aggregation. I don't remember if that's what it was called. Maybe it was called continuous queries. And so we would write raw data, like basically take the log data, turn it into JSON, write it to InfluxDB, and then when we needed to query it, we would do these aggregations on demand. And well, actually, it wasn't really on demand because there was this continuous query that was running and populating new things. But what turned out to happen is that we didn't really work on this project at all for like the next year and a half to 2 years. And by the time we got back around to it, by the time we started collecting feedback from people and they were saying, hey, this is really useful, I wish you would add these sorts of things, we had moved on to other projects and all this other stuff. But at the same time, InfluxDB had really come into its own. It had changed its data storage layer, at least 3 different times. They actually eventually wrote their own database that was specific to time series, like underlying data storage. And so when it came time to start implementing new features, we were kind of stuck, right? Like we could try to migrate to the new InfluxDB, but we're going to have to solve this problem of either double writing for a while so that we can populate the new database. And the reality was we would still have to operate our own InfluxDB cluster, where something like Postgres is this world-class offering that we have at Heroku. And if we could take advantage of that, that would be much better for us operationally. We wouldn't have to, wake up at night if a disk went down or something.
Yeah.
And, much better from like the perspective of like, there are experts at Heroku that are Postgres experts, and we can just like, take all of their knowledge and implement something that should work for us. So we basically gave up the idea of storing raw data at that point once we realized that maybe what we should be doing is storing it in Postgres. We can't store raw data in Postgres. It'd just be way too many points. And so we devised kind of a sharding strategy and a partitioning strategy. So we would store each day of like 1 minute data in its own schema, like Postgres schema. And that allowed us to like be able to drop the entire schema every time we wanted to like clean up, right? So one of the interesting things about time series data is it accumulates so fast, and like you almost never are going to need the 1 second resolution time series data a year from now. So people clean up data and they roll it up into different time frames. And so we were doing that too, but we wanted to make it easy because, as anyone who works with Postgres knows, having one table that you do large deletes in is just not the greatest idea. Like if you try to delete millions of rows, you're probably not going to have a great time. If at the same time you're trying to write into that table as well. So that was kind of the impetus to move. We chose Kafka, as a way to have some sort of reliability. There might be like a Postgres maintenance window that we're going to have to solve. Otherwise, we're just going to lose data, right? Like if Postgres goes down or something, then what do? If you put it in Kafka, you can just replay it and it's no big deal. There might be some delays, but so what? You'll eventually get the data. So around the same time that we were doing this, the Heroku data team, the team that actually operates Postgres, the team that was at the time trying to release Kafka, they also do Heroku Redis. They wanted to start storing time series metrics in a similar way to what we're doing. And so they've actually recently launched data.heroku.com, which gives you a little bit more insight into the data stores that you have. But they were starting to investigate using Cassandra with, they looked at a few things. One of the things that they actually went with was this thing called newts. And newts had the same sort of problem where, well, I don't know if it's a problem, but for them, it was a problem where they would put raw data in, and when they queried it out, they would do the aggregations. And that led to some really, really slow loading times for any of the pages and any of the graphs that they were trying to go for. And our strategy was to store kind of like data in the same object. So anything that's related to memory will be stored in one object. Anything that's related to request latency will be stored in one object and serialized to like its own topic. And so they kind of liked that idea. And what they decided to do was use our aggregation strategy of a topic per data store for them, store all of their metrics in one object, and aggregate everything like in advance in the same way we're doing it. But doing that, they wouldn't actually be able to use Postgres, for the same reasons that we couldn't. And they basically said, okay, well, we're going to have to run a Cassandra cluster either way. So why don't we run Cassandra for you? You guys switch to using Cassandra as your data store, and we'll share the same pipeline. And so my very, very motivated colleague at the time, in his spare time, after hours, he was just like cranking on trying to do this because we had other projects going on at the same time. He worked with them closely and, basically rebuilt a lot of what we had to support Cassandra as well, to support them. And at the same time, like during our transition, we were writing to Postgres, we were writing to Cassandra at the same time. And eventually the Heroku data team said, okay, you know what, we're getting rid of newts. This stuff is solid. And we said, okay, well, we're still, a little bit skeptical, but eventually we turned off our process that wrote to Postgres and haven't looked back since. That was actually just in the fall.
That's cool. So that is a great explanation of how you got to where you are in the database side of things. I want to dive into the Kafka a little bit more. So Kafka is this buffer that you're using between the application health data production and the end storage in these aggregated fields in Cassandra. Is there anything interesting going on in the consumer producer strategy of, what's going on, I guess? So, for people who don't know, Kafka has consumers and producers. So you're consuming stuff on the health data side for the applications that are running on Kafka, and then you're producing it out you're producing it and it's getting aggregated into these other topics, and then ultimately the aggregation is getting produced out into Cassandra. Is there anything else interesting going on in the Kafka layer?
Yeah, so I roughly described the way we lay out our topics. I think one thing that really should be stressed is how great Kafka is, right? I'm sure you've had lots of people on the show that have said the same thing, but
for sure,
when we were using InfluxDB, we were basically just had a web service that read or that received logs, turned those into JSON and wrote them right out. So if we did any sort of deploy or did any sort of anything or had any sort of outage or InfluxDB we couldn't talk to for some reason, we would just lose that data. And Kafka, adding Kafka into the mix, the only thing that we have to worry about is making sure that the data that we receive gets to Kafka. And as soon as it does, we can just be sure that we're going to have that data for good, for as long as the retention policy allows, which is like super killer. And I really cannot, explain how great that is in terms of a reliability story. So yeah, really the zigzag approach that I mentioned is the only thing that we're really doing. So for instance, again, the load averages that we get go into a load averages topic. The request latency that we get goes into a request latency topic. And, we basically treat Kafka as reliable Unix pipes, right? So we have one process that produces, another process that consumes, and then just pipes that out to, Kafka again. So all of our consumers and producers are just really, really dirt simple. They do some sort of summary usually, but that's about it. And all of the summary stuff just gets reused. So we have the same summary gets used with the same summarizer gets used with different parameters for the 1 minute versus the 10 minute versus the 1 hour. So just consistency and convention has made it really, really simple and really, really easy to work with. Now, there's a little bit of difference for the monitoring stuff, because we use Kafka also to kind of replicate out different states in terms of, let's say, we'll store settings and stuff for autoscaling or settings and stuff for our threshold alerting in Postgres. But before we save that, we'll actually write it to serialize it and write it to Kafka, such that some of the other processes that we have can be updated to reflect their in-memory state can be updated such that they can do their jobs. And we use for that, like that's the only place that we actually use a feature of Kafka called compacted topics, which is kind of like having a database in a stream processing system. They, it's kind of hard to explain, I guess, but you can be assured that Kafka will take every step or not really every step, but it's pretty good at basically storing one copy of, a value that you put in there with the same key. So it works pretty good for kind of replicating state.
Yeah. Well, and so for those who don't know, I think most people listening to this probably know, but Kafka, the reason you're praising Kafka so much is because it really was I don't know if it was the first, but it was the first message queue, distributed message queue that provides so much reliability that really caught on and really got a lot of people in the open source community excited. And early on, it had all these applications to big data pipelines, I guess, if you want to use that term. But as time has gone on, it's really become this crux of a lot of systems, and the people are using it in an increasing variety of ways. It's not just this, like, I don't know. It has grown in usage and adoption, and there appears to be no stop anytime soon for how popular Kafka is.
Yeah, no, totally agreed. I mean, there's a conference now, like Kafka Summit, that is just about Kafka, right? So you have this one product that has its own conference, and not many products can say that, which is kind of cool.
Yeah. So let's talk about the health check side of things a little bit more, because we're talking about this data that gets produced by all these applications running on Heroku. It gets piped through Kafka, gets dumped into Cassandra. But as far as the health check data itself, what exactly is going on there? Like, how is that data being collected? What is the process doing that is pulling that data? And I think you said it's running at 60-second intervals?
Yeah. So, I mean, we're aggregating stuff at 1 minute. So for instance, we have, I don't know if this is really the question that you're asking, but like the health checks that we're doing, there's kind of two. We're doing, error rate, and we're doing latency. And both of these are for like web processes. So not everyone sets up, alerting on Heroku. As much as we would love for that to be the case, not everyone has done so, either because they're using something else or they just don't know about it. But basically what happens is we have a process that runs, and it consumes the 1 minute data for the router statuses, and it's actually the same process, and there's another consumer set up in that process that just reads latency data. And it will filter out data that is not relevant and data that is relevant. That's what I was talking about with that compacted Kafka topic. Like, this process is programmed by reading that Kafka topic to make sure that it understands what data is relevant to different checks. And so it basically reads so for error rate, it reads the status codes, which we call throughput internally, and basically computes, like 200 responses versus 500 responses, and outputs an error rate. Latency, it'll do the same sort of thing. Like, we know what the threshold is that you're looking for. Same with error rate. And if that threshold is breached, we will, on another Kafka topic, send the result of that. Like, it failed, right? This error check failed at this time. This was the value of the thing that was over the threshold. And we have another process. We call it monitor manager, I think. And the monitor manager basically sits there, reads this topic that provides these check results, and maintains a state machine for each one of those monitors. So in the case of alerting, it's as simple as, okay, it was okay. The test failed, so now it's fault. Like, now it's at the fault state. If it's configured to send an email or do some other sort of notification, then it will do that. It'll write down that it did a notification, and then it just kind of sits there and keeps watching. And if the state changes, it does the appropriate thing. Autoscaling is a little bit different in that the state machine is much more complicated, and the check involves more data. Like, it's not just one topic that it's reading. It's reading, it started off by reading multiple topics and trying to merge together. We decided that was a little bit too complicated, so we're actually just going to Cassandra now and saying, okay, well, give me all of the data that we need, perform the check, and then write the result of that check to update the state machine.
So let's, I guess, zoom out a little bit. Can you explain the health conditions that will cause you to autoscale? Like, maybe explain what is going on end to end in a situation where that will lead to an autoscaling event.
Yeah. So the current way in which we do autoscaling. So yeah, sorry, I kind of threw in there what we do for alerting as well. Autoscaling, like I said, is a little bit more complicated, but the only data that we actually use right now for autoscaling is your response time, the P95 response time, the number of requests that you're making, errors, or the number of requests that you're serving, be it errors or successful requests, and the number of dynos that you currently have. And what we do is we utilize Little's law. And so Little's law is this thing from queuing theory that basically says the number of, let's describe it in terms of like a bank. So you have a queue, right? A queue of people that are waiting to be processed. They have some sort of deposit or something. And you have some number of tellers, right? Some number of bank tellers that can concurrently process each customer. So those customers have a time that it takes to do or to process one customer, and you have this like arrival rate, right? So you can think of like the arrival rate in queuing as throughput. You can think of the latency as the time a teller takes to actually make a deposit or withdrawal or whatever, and the number of tellers is that. So these things are interrelated into this relationship that some guy whose last name was Little, made famous. And what we basically do is we look at how many bank tellers there are at a given minute processing requests, and so like what the actual number of bank tellers is versus what the theoretical number of bank tellers would be if the latency was the value that you set, right? So Heroku Autoscaling works by simply setting a latency that you wish to respond in, right? So if your app starts responding greater than that latency, then we'll try to scale up and get it back down to that latency. So we have this relationship between what the SLA bank teller count would be versus what the actual bank teller count is at a given time. And we kind of just put that into something called an exponential weighted moving average. And we plot a regression line. And the slope of that regression line is going to give us whether or not it's okay to scale up or scale down. If we use the parameters that we get at that regression line, the slope and the y-intercept to, use that as like a prediction. So the current slope, the current y-intercept at x equals 5 minutes, say, will tell me whether or not I would have more or less capacity, and whether or not I should scale up or scale down. I guess that's kind of makes sense. I don't think I've ever tried to explain it in terms of bank tellers, but
well, first time for everything. Next time we'll do the dining philosopher's metaphor. So there was this interesting episode I heard of Software Engineering Radio recently that was talking about debugging distributed systems, and it was an interview with somebody from PagerDuty who had this difficult problem that occurred because a health check was lying, and so it was so fascinating how they had to dig into Zookeeper and TCP, but ultimately, this was kind of a scary problem because they needed this distributed systems expertise in order to solve it, essentially because there was this, at a high level, a problem where a health check was lying. Has that ever happened to you when you were building autoscaling and you had something that was incredibly difficult to debug, perhaps because a health check was lying?
So I don't want to say that a health check was lying, but I think that would actually be kind of a lie. We've misconfigured health checks before, like most people have done in the past. So one of the things that we do to monitor how autoscaling is working is we have a canary, and the canary basically tracks how many dynos are currently running, and we have an alert set up in Librato that says, okay, well, in this given 60-minute interval, did the number of dynos scale down to 1, which is what the minimum is set to, and it's supposed to say, did it also scale up to 3? But what it actually said was less than 3. And that led to a situation where autoscaling, we didn't discover that autoscaling was turned off in some cases due to a bug in serialization. I mentioned the idea that we store all of the parameter values in Postgres for all of our different checks. They get pushed to Kafka, right? And so it took us a while to figure out what was going on, but it turned out that in one spot, we actually serialized all of the data properly for autoscaling to ship out to the processes that do the checking and like the autoscale test. In another process that we use to kind of sync up things every now and then, we didn't serialize properly. So we ran this thing to clean up and make sure that our state was consistent between Kafka and Postgres, but it didn't reserialize all of the data properly. And so autoscaling stopped working for a number of apps. That's really the only thing that we've had in terms of autoscaling. In terms of alerting, like similar things, but we don't have this problem where we're using Zookeeper heavily. The Kafka 0.9, I think, started providing a way to store offsets like in the protocol itself. So I think Kafka actually uses different Kafka topics to store state about where you are in terms of like consuming and in terms of consuming and like groups and things like that. So we don't actually deal with Zookeeper directly. It's completely hidden from us. So we haven't had any sort of like weird thing related to that.
Yeah.
The other thing to mention here is I think, distributed systems are really hard, and debugging distributed systems are really hard. So maybe what we should all just go do is go surfing instead,
You are building a data-intensive application. Maybe it involves data visualization, a recommendation engine, or multiple data sources. These applications often require data warehousing, glue code, lots of iteration, and lots of frustration. The Exaptive Studio is a rapid application development studio optimized for data projects. It minimizes the code required to build data-rich web applications and maximizes your time spent on your expertise. Go to exaptive.com/sedaily to get a free account today. That's exaptive.com/sedaily. The Exaptive Studio provides a visual environment for using back-end, algorithmic, and front-end components. Use the open source technologies you already use, but without having to modify the code, unless you want to, of course. Access a k-means clustering algorithm without knowing R, or use complex visualizations, even if you don't know D3. Spend your energy on the part that you know well, and less time on the other stuff. Build faster and create better. Go to exaptive.com/sedaily for a free account. Thanks to Exaptive for being a new sponsor of Software Engineering Daily. It's a pleasure to have you on board as a new sponsor. So we've been talking about the pipeline between the health check and the data being propagated to the database, and then the potential triggering of an auto-scaling event. What about the actual auto-scaling event? How does that occur? What happens during an auto-scaling event?
Yeah, not a lot really from our perspective. We actually see that we need to scale up or scale down, and we issue a call to the Heroku API. The stuff that we do, we try to stay out of the platform as much as possible and make it external. Heroku has a long-standing tradition of allowing people to use the API to do everything that you would need to do in the platform. And so I mentioned before, like this concept of add-ons. We try to kind of act like an add-on, although we don't really use the add-on APIs to set up like users and things like that. We kind of have the ability to do that on our own. If you're interested more in how the platform actually adds a new dyno, I can talk about that.
Sure, that's certainly an interesting question because, well, I think of Heroku as this giant cluster of computers, and you've got applications who throughout the day are scaling up and down, and the cluster as a whole has an aggregate that is going to shift up and down. So as a whole, the Heroku platform seems like it has to make a lot of interesting decisions about how to scale up and down.
Yeah, so I mean, I should prefix this conversation or like the answer to this question with I'm not a platform engineer. So my understanding of this is not nearly as good as someone else's. But I mean, what it basically happens is we have a lot of things talking to each other. A lot of different systems are involved here. And so we make a request to the Heroku API. The Heroku API, the application that runs that, will make a request to what's called the KPI, which is, I think the K probably stands for kernel, which is what we kind of call like the underlying Heroku platform internally. And the kernel API, there's a system that's basically in charge of all of the orchestration around spinning up dynos, scheduling where they should go, what machine has the ability to host a dyno. And right now, we're not scaling, or we're not doing auto scaling for like 1 or 2x dynos. So you only ever get a dedicated dyno. So basically your own Amazon EC2 instance running some of our stuff and your application. But on the shared runtime, what's referred to as the common runtime, they maintain a Slack pool. So they might have 100 dedicated dynos at any given time ready to go and ready to just deploy your code and run it. In private spaces, which is a newer product, it takes a little bit longer to get a dyno. And that's mostly because we can't, I mean, there isn't like a shared cost. Like your private space is private, right? And right. You're basically paying us to operate a VPC with Herokuisms, like an Amazon VPC. So it might take like 1 or 2 minutes to start a dyno. I think they do have a concept of Slack pool, but it's not super widely used as far as I know at this point.
Now, zooming out to the perspective of the developer again, what are the scalability bottlenecks that a developer is going to have to solve themselves, even if they're on a platform as a service or infrastructure as a service? They've got auto scaling. I sense that there are certain scalability issues that the platform is probably not going to take care of for you. You're a developer, you have to still keep this in mind. What are those kinds of bottlenecks?
Yeah, so I think probably the biggest bottleneck here is like your reliance on a database. Postgres, like interaction with Postgres probably accounts for a decent number of our support tickets, and the reason for that is, no database is a magic box. Well, maybe Cassandra, like given the amount of write throughput you can get and things like that. But even still, you're going to run into limitations in Cassandra unless you design things in the way that, Cassandra is meant to be used. And so I think probably like a big pain point for people running on a platform is, they might think, oh, well, I run my application, I run a Postgres database, and everything's just going to be fine. When in fact, like if you don't actually plan out like how your data is laid out, it's going to be painful no matter what. And as much as I'd like to say, hey, we can just auto-scale databases, I don't think that's necessarily a reasonable thing to do. If you're using Postgres, you probably want to take advantage of transactions, and adding like another Postgres box is just not going to solve that, right? You're going to need to know that you're doing that. You're going to need to shard and write data to like a specific instance so you know where it's going to be, or things like that. There's maybe some availability for us to scale like a Postgres database vertically. And by that, I mean, put it on a bigger box with a bigger disk, which I think actually Heroku Postgres already does. I think it will grow the disk. I could be wrong, so don't quote me on that.
Okay.
But like that sort of thing might be more possible. On the other hand, I don't know how you could actually do that without downtime, unless like the infrastructure that we're using supported, adding CPUs at any given time or memory, which I don't know of any infrastructure right now that's that elastic, right? Everything is still kind of using this concept of like Zen, right? It's like it is an instance, and it, as far as you're concerned, it's hardware sitting in a data center, and it might be virtualized, but it has sort of the same properties, at least in terms of resource allocation.
You touched on this a bit earlier about Heroku having these pools of dynos that are ready to be allocated to somebody who spins up a new application, or perhaps somebody who is scaling their application. What are the other interesting aspects of scaling Heroku itself?
Scaling Heroku itself. It's an interesting question. I think the interesting things are yet to be realized, really. We've been pretty good about making things horizontally scalable, relying, like making sure that if there's if we think that a database is going to be bottlenecked, we'll try to shard upfront, or at least design it with sharding in mind, so that we can migrate to a sharded strategy in the future. The thing that I'd like to see us consider doing, and we probably will do in the future just out of necessity, is make smaller Herokus in more places, right? So right now we operate in one of the EU Amazon data centers, and we operate in US East. It'd be really cool if there was common runtime available, like maybe it was US East 1 and US East 2 and US East 3 and US East 4, and they were in desperate, like availability zones in AWS. And if we could do something like that, then maybe it's the case that the current size of Heroku right now could operate in one of those smaller regions, or what we would call regions. And then, we can basically horizontally scale those regions out as big as we necessarily need to scale the rest. I'm not really sure how that would actually work without significant changes to the way in which our API works, the way the KPI works. But again, that's also not my wheelhouse at Heroku either. So I'm sure someone is thinking about this, and has a much better solution than I do.
Have you seen any interesting traffic patterns for how applications across the Heroku platform are scaling up and down throughout the day?
It's funny. It's one of those things that is not really surprising. Like the internet wakes up at 8 a.m, goes on a website, and you see traffic throughout the entire day. At some point in time, the traffic dies off because people go to bed. So like the different patterns that I've seen have been mostly around that. It's like, okay, well, yeah, it's obvious that people are sleeping and waking up. So it's less surprising than anything to me. But I haven't seen any I haven't actually even seen, I'm sure it exists, but I haven't seen like a flash sale application. This idea of at noon, we have a sale and everyone comes at noon, but the traffic just goes away. And actually thinking about it, I think our auto-scaling solution would be silly for that. I think you'd be much better off saying, okay, well, I know that my traffic is going to be high at 12 o'clock. I'm going to make sure that I have, 20 different dynos already scaled up and ready for that sale, and then I'll scale them down. So yeah, I guess the holy grail of auto-scaling would be to be able to anticipate that over days and days of understanding traffic patterns. But
sure,
that's not a problem that I yet know how to solve. So
you're an operational experience engineer at Heroku. What does that title mean?
I'm still trying to figure that out, to be quite honest. But I think one way to look at it is, there's this concept of SRE, site reliability engineering, and usually they have the customer's best interest in mind, but they're not directly working with a customer, right? So they're working to make sure that the platform and the applications that are building a platform are up to snuff and reliable. I think in a lot of ways, the operational experience team at Heroku is trying to be the SRE team for our customers, right? And trying to build tools that stand in for an SRE team at our customers' organization so that they don't necessarily have to have one. Heroku by itself already kind of eliminates a lot of the work that a DevOps team might do, or an operations team in general. And if we can provide more tools, then the ability for a Heroku customer to focus on their app instead of operations tasks is what we're trying to maximize here.
Do you have any final parting lessons that you learned from building the autoscaling project?
I think the best lesson that I have is to try to make things as simple as possible. We were able to go pretty far by thinking of Kafka as a Unix pipe, right? Like, we read data in a very simple manner. We write data out in a very simple manner. And that's led to us being able to build like these simple libraries and simple frameworks that allow us to just, cobble things together without too much trouble. We rely on Kafka and we rely on Cassandra, and those tools are meant to be relied on. So you might as well just assume that they're going to do what they're supposed to do, and it should be pretty good. Now, of course, you're going to run into bugs now and then, but you take them in stride and deal with them when you deal with them, or deal with them when you get them.
Andrew Gwozdziewycz, thank you so much for coming on to Software Engineering Daily.
Well, thank you so much for having me.
Thanks to Symphono for sponsoring Software Engineering Daily. Symphono is a custom engineering shop where senior engineers tackle big tech challenges while learning from each other. Check it out at symphono.com/sedaily. That's symphono.com/sedaily. Thanks again, Symphono.
Wow.